So we'll pick up where we left off in class. And we have done two definite integral problems. And then we've taken the derivative of the function with respect to x, and we have found out that if we take the derivative with respect to x of a definite integral from some constant 2x of f of t dt, we end up getting the original function, but in terms of x. Here we started with t, and once we were done taking the derivative of the definite integral, we found out that the derivative of the definite integral was equal to x. So we could conclude, based on our two examples, that the derivative with respect to x of the definite integral from some constant, that is, a is a constant, of f of t dt will equal f of x, which is the original function, but instead of t, we have x. So what that means is that if that statement is true, which is the basis of what is called the fundamental theorem of calculus, if this statement in the cloud is true, then that means that the definite integral from a to x of f of t dt has to be an antiderivative of lowercase f of x. Because if I take the derivative of the antiderivative, I should get back to the original function. So we're going to call this antiderivative function capital F of x. Our function that we start with is lowercase f of x, and the antiderivative is capital F of x. So, given that that must be an antiderivative, then this statement must be true. The definite integral of f of t dt from a to x will equal capital F of x plus c. Because if you remember, when we dealt with antiderivatives, we had to always consider a constant being added, because the derivative of capital F of x plus c would be the same as the derivative of capital F of x alone. And then we need to find that constant. And so the way that we'll do that is we'll plug in a value for x such that we know the answer to this definite integral. So we're looking at the definite integral from a to a of f of t dt, which we saw in our definite integral properties, that the integral from a to a of any function would be 0 because there is no width. So this 0 must equal capital F of a, because that is the value up here as our upper integration limit, plus c. And now we can solve for c, so c must equal negative f of a. And what that leads us to is the form of the fundamental theorem of calculus, the way that it is seen most often. So that's what is in this final cloud here. The definite integral from a to x of f of t dt will equal the antiderivative, capital F, of x, notice that is the upper limit of integration, minus capital F of a, which is the lower limit of integration. What this means is that we now can find the area under curves of things like a cubic function or a fourth degree function or a sine function, where it may not be a simple geometric formula helping us to get to the area. So the process that is going on in this fundamental theorem is that if we are looking for the definite integral from a to x of f of t dt, you will take the antiderivative of lowercase f, that is capital F, you'll evaluate it at x and a, and you'll subtract to get the value. Very big day. Fundamental theorem of calculus. You'll see me abbreviate this with FTC. So now let's see how we use it. So, let me get rid of this. And we'll put it back up there. Okay, so let's say we were asked to find the definite integral from 0 to pi of sine x dx. And you're asked to use fundamental theorem of calculus to find the definite integral. All right, so the first thing we need to do is take the antiderivative of sine x. So we ask ourselves, what did we begin with to get sine x as our derivative? And what we began with is negative cosine x. And we should recall that it wouldn't just be negative cosine x, it would be negative cosine x plus c. And you'll see this notation where I draw a straight line, which means to be evaluated from x equals 0 to x equals pi. So now we're going to plug in pi for x, plug in 0 for x, and subtract. Okay, and when we do this, we get the negative cosine of pi plus c minus the negative cosine of 0 plus c. Well, cosine of pi is negative 1, so we have the negative of negative 1 plus c minus negative cosine of 0 is negative 1, and we distribute the minus through the entire second term. So we end up with minus c. Please notice that our constants cancel. And that will always happen. So when you are doing a definite integral, it is actually not necessary to put in this plus c from now on, because those constants will always cancel. So with antiderivatives, you will have a plus c, but within a definite integral, you will not. So here we end up with 1 plus 1, and our definite integral comes out to be 2. Just like we saw in the previous section when we were told to use the integral from 0 to pi of sine x dx equals 2. So we've just verified that. All right, let's try one more. Here we're doing the definite integral from 1 to 3 of x squared plus x dx, and we want to use fundamental theorem of calculus to do this. So we start by taking the antiderivative of our integrand, and the antiderivative of x squared is x cubed over 3. Plus the antiderivative of x is x squared over 2. And this is to be evaluated between 1 and 3. Okay, so we plug in 3 for x, and we get 3 cubed over 3 plus 3 squared over 2, minus, and then we plug in 1 for x, 1 cubed over 3 plus 1 squared over 2, and then we just calculate those fractions to come up with 76/6. So, again, fundamental theorem of calculus allows us a way to find the area under curves that may not be as simple as geometric figures. So it gives us a great deal of power to find the area under many, many infinite number of curves. And that should do it for today. So please use this video to help you with your homework, which is on the website. Quiz tomorrow, Tuesday. I will be in early before school if anyone has any need for help.